question it, not pessimistically, but what's a better word? Critically. Critically, which is not a negative thing. It's a careful thing. Okay, I see the headline. Harvard study confirms. Now, when I hear the word confirms, that makes me think it was already done somewhere else and they backed it up and replicated it, which is kind of the hallmark of good statistics. Let's talk about why. You've heard studies being replicated, yes? Studies being replicated. Why is it important to replicate a study? Go ahead, Tim. Let me hear from you. Go ahead.
That's how we found it changes drastically from time to time or whatever.
You need markers?
Oh, here they are.
I don't know, once isn't good enough because
why isn't, do you hear what Jim just said? Why isn't once good enough?
things change.
Suppose for example, let's throw this back to what we've already been talking about, yes? Let's say we do a study with a fluoridated kid. Now what's the average IQ? 100. Well, by definition, average is 100 because that means your chronological age and your mental age sync up in some way on some assessment. Let's suppose that we run an IQ study. I've actually got some data later on for us to test on this very
IQ studies are so ridiculous.
Lauren, hold that thought. You're about 3 steps ahead of me. I'm going to just on the test itself, I want to focus now. Just on the mathematics of what Tim just said. I want to come back to the biases in the study, yes. But I want to focus on the mathematics of why replicating a study is important. Because this is huge. This is huge. So here's the deal. Here's a sliding scale of IQ. Suppose 100 is there. 100 is there. That's the average IQ. And we do a study on IQ in these children with fluoridated water supplies. And what do we notice? What do we notice? They're here. And this is a study replicated by Harvard in 2013. Hold! Time out! IQ is lower in children with fluoridated water supplies. True based on that. Statistically true based on that. Statistically significantly true. Assuming they're supposed to have an IQ of 100. Yes. I mean, that's statistically significant. It's not touching 100.
But it doesn't prove causality.
Good. Hold that thought too. You're getting into Lauren territory there at the end. I'm trying to focus on the mathematics just right now, okay? Just right now. I want to come back to bias in a second, which I love. It's very important. But right now, just the mathematics. Somebody over here was saying something. I cut you off. I'm sorry.
I said you have nothing to compare it to.
Well, let's suppose the 100 was the comparator. Now, there might have also been a control group, Skylar. Maybe there was a control group as well. And the control group, assuming that headline was correct, there's 2 ways you can test with a control group. One way is to slap a secondary interval that consists of the control group and see if it touches or doesn't touch that one. We've talked about this before, yes? So that might be the fluoride group. This might be the experimental group, or the control group, excuse me, the ones without fluoride. That's one way of looking at it. There's another slick way of looking at it that I want to come back to as well, and we're going to talk about this quite a bit in this class. One way is to take both groups. Don't put them together, but put their statistics together. So you calculate the average of the fluoride group, and you calculate the average of the non-fluoride group, and you subtract them, the averages from each other. And you have to do this properly. You can't just subtract the average. You have to wait with the standard deviation, which I want to get into as well. But why would you subtract the averages? Why would you subtract the averages to see if there's a difference? Say that again. Oh, good. We should take care of that even before we do the subtraction at the end, because the outliers could skew the averages up or down. Thank you for that. More on that to come.
On average of the partner there.
If they're the same on average, and when I say the same, I mean statistically the same. They might not be exactly the same, but they're close enough to be statistically the same. If you subtract their averages, what number should that give you ish? Should give you 0, yes? Should give you 0 if they're the same. If they're not the same, and you subtract their average, 0 won't be in whatever interval you correct. So this is one way of looking at it. Another way of looking at it is to compare it to 0, and then see which side your interval falls on. So suppose you subtract the fluoride kids' IQs minus the non-fluoride kids' IQs. And that comes back looking like this. What does that tell you about the fluoride kids' IQs? It's got to be lower, right? If you take smaller numbers and subtract bigger numbers. If the fluoride kids are being subtracted minus the non-fluoride kids, so smaller minus bigger is going to yield negative numbers, yes? That would be conclusive statistical proof that fluoride's damaging IQ?
No.
No.
Statistical proof. I'm not talking about bias, I'm not talking about sample bias. I'm talking, if you've done the controlled experiment, and you've eliminated every other variable,
It proves that they have lower, not that it caused it.
if you, listen to my if, if you have controlled for everything else, you have statistical support. I'm not doubting what you're saying, Deanne. I'm saying if you have control. Realize that the if I am saying right there is almost impossible to accomplish. But I'm trying to focus on the mathematics here, not all the subtleties. I love that you guys know the subtleties. I love that. And I'm not saying it's not important. I'm trying to answer Tim's question about replication, which we're getting to here. Now, if it flips the other way and we do fluoride kids minus non-fluoride kids and they end up here, that's statistical support that fluoride's actually increasing IQ. Assuming it, Deanne, focus on the math. Now, what if this happens though? What if this happens?
Then you can't prove anything.
Then you can't make any claim whatsoever. You can't make, because 0 is in there. If we're on this side of the interval, it looks like fluoride is worse than non-fluoride. If you're on this side, it looks like it's better. If it's right here in the middle, you can't tell where the fish is swimming. So you compare it to 0. Now here, mathematically, why is this a better treatment than looking at 2 separate intervals? This is back to Tim's question. I wanted to set the stage for that. The question was, why is replication better? Well, what's the problem with having 2 separate intervals like this?
They're different every single time.
Say that again?
Well, because all of those little things are on average your data points in between here.
Correct, absolutely.
So, by looking at that, those bars, every single time you're going to redo the thing, are going to shift.
Boom. That, hopefully, that's sampling error, and we expect that, yes?
Yeah.
You also have inferential data with the second one. You have like a yes,
Good.
no, maybe.
Good, very good.
As opposed to
Yeah.
here's
So
your
by
data.
recreating the project, the experiment, you're proving, if you get the same results over and over again, you're just making it concrete. Yes, fluoride is.
Hold that thought, Kate. You're about 3 minutes ahead of my mathematical argument. Can you hold that though? I
Yes.
love that. How confident are you in this confidence interval right here? Not usually 95%, yes? 95% confident. How about this one?
Probably.
Yeah, right here. How about this one? No reason to think it's not 95%. So, somebody say it over here. Skylar!
You would have to square 95% to get the actual total confidence.
Say that a little louder.
You would square 95% because that's the total confidence.
Here's your throwback to 243. The reason why this keeps 95% confident, this actually sacrifices confidence. Because in order for you to be correct in your conclusion, this one has to be correct. And this one has to be correct. This could be an error, yes? This one could be wrong. That one, they could all be wrong. But the only way you can believe that there's a difference between this one and this one is if they're both correct. Now that happens 95% of the time, yes? Well, that means this one's correct and that one's correct. And what does the word "and" mean in statistics? It means to multiply. So really, your total confidence in this study is actually 95% squared, which is less than 95. Michael, go!
So because it's 95% confidence, would 2.5% be on the other side? So couldn't you add that too to make it a little bit more confident? So it'd be 97.5.
You can't do, well that, you're getting the idea of a one-sided interval now, which I love. But you have to recalculate the ranges of the intervals. You can't just tap it on after the fact. You have to calculate it with that in fact. Does that make sense? And more on that today as well. That's part of the calculation of how far out you go or how close in you come. Good, very good, thank you. Does that make sense, friends?
Yeah.
So, if you buy that, you can see it's always beneficial if you can to do one calculation on whatever data you have. And if you have like 5 and 6 and 7 data sets, it's often much better to combine all of them down into one what's called test statistic, which you can then slap onto a number line and look and compare to 0. So very often you'll see us comparing things to 0 because that's the least, it's the least loss of confidence, if that makes sense. You're always going to have some uncertainty, right? You're always going to have some uncertainty. But the kicker is, how can you minimize that uncertainty? Okay, we're almost answering Tim's question, I swear to God. Because we haven't talked about doing the study more than one time, have we? So, let's suppose, can I take this one away? Okay, hold that thought. Are you sure? Is ready for this? Go, go, go.
So the 95% confidence square.
Yes.
Is that going to the one on the 100 or the?
That's this one.
Okay.
Because
okay,
each of
you're
these
saying
is
it's the other
95.
one.
No, this
Okay,
one's
so we're
gold.
good. Then we're
This
good.
one's gold. This one's still at 95% confidence. And every time you add an interval, you have one of your exam questions actually deals with this for next week. If you keep just tacking confidence intervals on to a study, well, let's look at Delaware, let's look at Pennsylvania, let's look at Michigan, let's look at this, let's look at this. Keep going. Every time you add an interval, you raise that exponent again. 3, 4, 5, and the confidence just buries after a while. And pretty soon, it's almost guaranteed
You're wrong.
that one of them, at least one of them is wrong. Thank you. Go, JC.
Okay, so I understand what you just said.
Good.
But the one on the right
Yes.
is in both. So how can you interpret that? Like it could be either or. So how are you,
How am I maintaining confidence?
well, no, how are you proving or how can you say it's one or the other?
Oh, love the question. Hold that thought, okay, JC? Let me phrase it a different way, okay? Let me start and stop. That's a great question.